All right, good morning, everybody. So as promised, we're going to cover all aspects of the electron-ion collider, experiment theory, and accelerated technology. And so we are very happy that today we have Christoph Montag from BNL who's going to tell us about accelerated technology for the AC. The floor is yours.
Right, thank you for the introduction. Yes, so I'm Christoph Montag. I'm from BNL, working on the Electron-Ion collider, and I know for most of you, the accelerator is just a hole in the wall that delivers the beam to your detector. Well, I want to show you that there's a little bit more to it, and only have an hour to do that, so let's see how far we get here. So this is RIG, right? You may be familiar with that. Consists of two storage rings, superconducting. Oh God, I don't have a real... The real laser doesn't work on this, right? Does it?
So this one.
I hate this. I hate the delay and everything. Yeah, no, it's okay. I'll try. Okay, so this is RIG. Brook. My God. Consists of two superconducting storage ring. The circumference is 3.8 kilometers or 2.5 miles if you prefer that. We have 6 potential interaction regions here, and we name them according to the clock. So 6 o'clock, 8 o'clock, 10, 12, 2, and 4 o'clock. Beam energies reach up to 250 GeV for protons or 100 GeV per nucleon for heavy ions like fully ionized gold. We have 110 bunches per beam, and this machine, I should say we had 110 bunches because RIG is being dismantled now. And it can deliver ion species from protons all the way to uranium. So we did that. What is unique about RIG is that the proton beam is polarized. 60% proton polarization has been achieved, and that makes RIG the world's only polarized proton collider. And the fun fact is that it exceeded its design luminosity by a factor of 44 over the years. It was in operation since 2001. It was turned off in February of this year to dismantle it or part of it and install the EIC in the same tunnel. So the EIC design concept, it's based on the RIG complex. We reuse the tunnel, and we also reuse one of the RIG rings, the yellow ring, as the hadron storage ring. We keep the injectors, ion sources, and RIG only, or the yellow ring only needs relatively few modifications to be useful for the EIC. The beam parameters in RIG are already pretty close to what we need in the EIC, except for the number of bunches. Do anything? No, it does. Okay, I had to shake it for some reason because the battery is bouncing around. Except for the number of bunches and the total beam current and the vertical emittance. So now to make it an electron-ion collider, we have to add an electron storage ring, 5 with 18 GeV, and its injector complex to this, and that gives you a center of mass energy from 29 to 141 GeV. When I quote energies, I always talk about protons because it's much easier than going over different ion species. But you can convert that. And then, of course, we need an interaction region where the two beams collide, where you put your detector and so on. The design aims to meet all the goals that are formulated in the famous EIC white papers, in particular the high luminosity of 10 to the 34 per centimeter squared per second and the high polarization. All right, the EIC design and performance parameters have been adopted from machines like RIG for the hadron beam and for the B factory KKB in Japan. We have performed simulations and beam studies to make sure that this is really realistic what we are doing. So we use RIG as a test bed for most things. So one thing that we tested here that's totally unique is that the proton beams or the hadron beams are flat. Normally, hadron beams are naturally round. We want them flat because the electron beam is naturally flat. That's an effect of the synchrotron radiation in the electron storage ring that flattens the beam, basically squeezes the vertical beam size, the vertical emittance to very tiny values. So we tested that experimentally in RIG. We need an emittance ratio of 11 horizontal over vertical emittance, and we tested that, and this is here the ratio that we achieved in the two rings. So we got something like 13 or so in blue ring and 8 or 9 in the yellow ring. So we claimed success there. We have reached our factor 11. So that's a world first that we demonstrated that, and that's the key ingredient to get high luminosity in the EIC. This is the layout of the EIC facility. So as I said, we use the yellow RIG ring, which goes counterclockwise as the hadron storage ring. We have a new injection line here from the AGS. Before in RIG, we injected right here. We need more space for the injection kicker, so we extended the line, and we will inject here at IR4, as we call it. Sets is still wrong, so the 5 to 80 GeV. Oh no, the electron storage ring is in the same tunnel that goes clockwise. That's the red ring here. And then we have a separate synchrotron, a rapid cycling synchrotron here in a 1.4 kilometer tunnel adjacent here to IR4 to inject into the electron storage ring. That thing cycles at 1 second, so we provide 1 bunch per second to the electron storage ring. I come back to that later, why we have to do that. And then, of course, there is the detector here, EPIC in IR6, and a possible second detector in IR8. This is the luminosity versus center of mass energy curve for the machine. So that's electrons against protons. Always our reference is protons because it's much easier. So here you see we indeed reach 10 to the 34 per centimeter squared and second luminosity when we collide 10 GeV electrons with 275 GeV protons. If we go higher in energy, we do that by increasing the electron beam energy. The electrons, when they emit synchrotron radiation, as we call it. So that is electromagnetic radiation. It's accelerated charge, right? They are accelerated continuously on the circle, so they emit. It's also, you can think of a dipole antenna if you want. It's the same thing, right? You emit radiation. If you go down in energy, then we are what we call beam limited. So the beam that goes lower in energy feels more of the oncoming beam. It gets hurt more, so we have to decrease the intensity of the oncoming beam. So the beam actually that we are, both beams survive. Otherwise, they would just blow up and get lost. And then at very low energy, we are space charge limited. That means we have to decrease the intensity because we have same charges in each beam traveling in the same direction. So they repel each other because they are the same charge. And of course, on the other hand, they are parallel currents, so they attract each other. If you reduce the energy, then the net force here that scales with 1 over gamma squared becomes larger. The beam blows up because the repelling charges basically overwhelm the attracting currents. Parameters for the highest energy here. I don't want to go through the list here. So that's again our reference point, 275 GeV protons, 10 GeV electrons. So we have a large number of bunches here, 1160. We have a large we have a large beam parameter, which we adopted from both RIG and the B factory. And what is interesting here in this machine, so we limited our parameters such that our so-called IBS growth time, that's the intra-beam scattering growth time, is at least 2 hours. So we have to counteract that. What happens there is all the particles in the bunch, they scatter off each other, and over time, basically, that leads to a blow up of the beam of the bunch longitudinally and transversely. If that is too fast, of course, then you get a large peak luminosity. Everything blows up in a very short time, and you don't get good luminosity lifetime. All right, so let's talk a little bit about the hadron storage ring. The HSR consists, again, of the yellow ring of Rick, basically, with modifications. And what we have to do is we have to insert what we call sleeves for this entire 3.8 kilometer long accelerator. So the reason for that is Rick is superconducting. The beam pipe is made of stainless steel. Stainless steel is not a very good electrical conductor. So the beam is bunched in short packets. It moves around the beam, around the ring. And so you have image currents that want to travel in the wall, but your wall is not really a good conductor. So what happens is if you send currents through a resistor, the resistor heats up so that the wall gets warm, and we can't cool that away with the helium plant. So we have a limit of half a watt per meter on average that we can cool away. If we don't do anything, if we just left the stainless steel beam pipes, we would have 5 to 10 watts per meter that we would have to cool away. So we can't do that. That's why we have these sleeves here. So that is stainless steel, copper plated, and the copper plating is then the good conductor that takes care of the image currents. And that's why we can get to the higher beam current, the higher beam intensity in this machine. We need new RF cavities for beam acceleration and longitudinal focusing. We have to have hadron cooling to create those flat bunches that I talked about before. So naturally, from the injector, the beam is round, the hadron beam. We want to make that flat, and so we cool the vertical beam size, basically. And I come back to cooling later. It's my favorite topic here in this presentation always when I come to the cooling. Then we need what we call crab cavity. This is really funny. We need crab cavities. I'll talk about that as well, and special magnets for the interaction region. And finally, a collimation system to protect the detector from all the debris that comes with the beam and from all the particles from the beam that want to get lost. All right, so I said before that we have this large energy range in the hadron storage ring that goes from 100 to 275 GeV for protons. What happens is we have to keep the two beams, the hadron beam and the electron beam, synchronized. So they always meet again. The beam comes in little packets and little bunches. So we have to make sure that they always arrive at the detector at the same point, at the same time. When I reduce the hadron beam energy, they are not really that relativistic. They change their velocity, and that makes a little bit of a difference. The electrons are always relativistic. They always have a gamma of thousands, so they always have the speed of light. For the hadrons, I have to do something. So the way, of course, if one of them is slowing down, we change the circumference. The way we do that, this circle is our beam pipe, and we change the radius of the entire orbit by plus minus 20 millimeters. Inside the beam pipe, we have enough room. So at 100 GeV protons, they're in the middle of the beam pipe, and then we move them to the inside of the ring. When we go to 130 is in the center. When we go to 100 GeV, we go to the inside. To 275, we go on the outside. And that's how we keep the beam synchronized. It has been demonstrated in RIG that we have enough room in the beam pipe, and that works. However, the experimenters want to go to even lower energy, below 100 GeV proton beam energy. And there we play a little trick here. We take advantage of the fact that RIG consists of two rings. And you see here that the yellow ring always moves from here. It's on the outside, and then it goes to the inside. So it's not really a simple circle. The blue ring here in this arc is an inner arc and the yellow ring is an outer arc, the difference in radius is 90 centimeters between these two arcs. So we, in 1 sextant, if we use the blue arc here, the shorter one, instead of the outer yellow arc, then that changes the circumference by 90 centimeters roughly. So the distance is 90 centimeters. It's 1 sextant, 1/6 of the ring. 2 pi equals 6. So that's why the circumference change is basically the radius change in this case. And yeah, that's how it looks like in the cross section. That's the electron ring. That's the yellow hadron ring. And then in this arc here, we have this. So funny. And then we have this blue arc here on the inside, so we can use that other arc to as a bypass or shortcut or whatever you want to call it. Okay, intra-beam scattering. So I talked about that before, already introduced that briefly. So the individual particles in the bunch, in that little packet, they are always focused by the magnets as they move around. So they always get kicked back to the center by the magnets due to the focusing. And that means they travel close by each other. They can scatter off each other. That's a heating effect, and that blows up my beam. I want to counteract that because that would cause luminosity loss, of course. If the beam is too large, you have less density in the beam, and you don't get any luminosity out of the beam anymore. Okay, so what do? I provide cooling. So there are different methods for cooling. So one of them is conventional electron cooling, as we call it. So we have this is really poor quality in this picture, but I hope you can see what I want to show here. So we have the ion beam or proton beam here. That's the green arrow that's going through here. So it goes on a circle, comes around and around. And then I have a high intensity electron beam that I merge with it here over this section. And basically what I do is I have my ions and I give them a cold bath. Every time they go through this cold, dense electron beam, they lose energy basically to the electrons. The electrons get replaced, so I heat up the electrons. I don't care. I dump them here and I always have fresh electrons. And that cools my hadron beam, so it shrinks actually. The disadvantage of this method is that the cooling time scales as gamma to the 5th power, so it really does not. This battery is moving inside. Okay, so it scales as gamma to the 5th power. And that means at high energies, this becomes a huge facility. So normally if you do that at tens of MeV, then you have something that you could put in a regular room, basically, that's a decent size. And thank you. I hope that works better. Yes, thanks. Okay, so at high energy, becomes difficult. So there are different methods then to do that. So this is my favorite slide here. Let's make sausages. And this is called stochastic cooling. So what happens is you measure, if you measure just the beam orbit, the offset at one location in the ring, and you take the whole bunch and measure it once, then yes, if on average it's not at the design orbit, it's not 0, basically the offset, you can correct it once and that's it. So you don't really cool. But the idea here is that you slice your bunches electronically. So, and that's what the sausage is. So the sausage on average is on the orbit, but every little slice of your sausage is a little bit offset. So let's assume that the white fatty parts are our particles in the beam, and the red around that, that's vacuum, right? So there's nothing in between. So I slice this thing. And now if I make the slices thin enough, then if I measure really carefully, then I will see that on average, my little fatty parts here, my particles, are not on the orbit. They have a little offset. So for each slice, I can correct that. I bring each slice back to the center. So now I'm done with that. And now what happens? The beam travels around the machine. And now I mix. And what I do is all these particles here, all these white fatty particles, they move longitudinally into different slices. So when they come around, every particle has changed its position relative to the slice, but not the transverse position. So now I measure again at each slice and I notice, oh, the average is no longer zero because it's a different subsets of the particles. So I measure again, I correct here again. If I do that frequently enough, it brings all my fatty slices to the center of the sausage. And so that's here the cooling time is proportional to the system bandwidth divided by the number of particles per bunch. So in typically these systems, they have a bandwidth in the gigahertz range, a few gigahertz, and that leads to 30 minutes cooling time or a billion particles. So we have a billion gold ions in an EIC beam or in a RIG beam per bunch. So that works. It does not work for protons, because for protons we have 100 times more particles, so that would take 100 times 30 minutes, 50 hours. That's not reasonable to do that. So we need a different system. And what we do here, we sort of build a hybrid of the two systems. So instead of measuring the positions of these slices and sending the measured signal through a copper wire or a fiber or whatever, we use the electrons themselves. So what we do is we have an electron beam, we merge it again with the hadron beam, and the hadron beam imprints its little imperfections onto the electron beam. So all the little slices there that are slightly offset, all this information gets imprinted on the electrons. Then we send it through a free electron laser as an amplifier. And then we bring it back with the right phase advance, basically, and merge it again with the hadron beam. So now the electrons kick back all these slices in the hadron beam. So now I have my stochastic cooling effect. And if I do that frequently enough, or in this case, a couple of minutes or so, then I also get the cooling. The difference compared to the conventional stochastic cooling is the bandwidth. I get tens of terahertz because I use an electron beam instead of amplifiers and copper cables and so on. So that's how I can cool the hadron beam. So now the electron storage ring. The electron storage ring consists of 6 arcs with a very conventional optics. We call the photocell, and 6 straight sections. The straight sections are used for detectors here, IR6, IR8. Again, of course, it's the same detectors that I showed for the hadron beam. The RF cavities are in IR10. We inject, this is also still wrong, I thought I corrected that. We inject in IR4 and cross over the hadron beam here. And we have a second crossover here in IR12. Because we have to have the circumferences of the 2 rings the same, so we can't have one ring on the outside all the time and the other one on the inside, so we cross over. And IR2 here we use for instrumentation and also for the cooler. So one interesting feature of the electron ring is that we have to keep the emittance constant. So normally what electrons want to do in a storage ring, if you change the energy, then the emittance scales as gamma to the square, gamma squared. And the problem is, of course, if I want to keep this here constant from 5 to 18 G, I have to do something. So we have 2 knobs to change that. One is the focusing strength in our ring. So what we call phase advance, we changed it from 60 degrees at 10 GeV to 90 degrees at 18 GeV, and then I get my design emittance of 20 nanometers roughly at both energies, despite the energy change. And for 5GeV, I have to do something else. So all the dipoles, all the bending sections in the electron storage ring consist of 3 magnets that are these 3 gray areas here. When I operate the machine at 10 to 18 GeV, I run all these dipoles with the same polarity, same strength. So I get a nice smooth curve here. When I go down to 5 GeV, I power the center dipole in reverse. So what I get here now is some very sharp bends that generate additional synchrotron radiation, and that increases my emittance at 5 GeV again to the 20 nanometers that I want to have. All right, the physics program for the EIC requires electron bunches with both spinelicities up and down that we then convert into longitudinal spin at the detector. And so how do we do that? We want that simultaneously in this machine. So there is an effect. Again, it's related to synchrotron radiation. That's the Sokolov-Turnoff effect. These electrons, if you just leave them alone, they would self-polarize over. At 18 GeV, it would take about 30 minutes to self-polarize. At 10 GeV, it's a couple of hours. At 5 GeV, it's hopeless because it also scales with I think it's also gamma to the 4th or 5th or something. The issue there is, of course, if I use self-polarization, they would all end up at the same spin orientation. I want to have up and down simultaneously, but they would all end up, let's say, with polarization up, so anti-parallel to the main dipole field. So the only way to achieve these spin patterns is to inject the bunches with the desired spin direction. If I want to have spin up, I inject the bunch with spin up. If I want spin down, I inject the spin down. But of course, they don't stay there, the polarization, because I can't turn off Sokolov-Turnoff. So if, let's say, my stable spin direction from Sokolov-Turnoff is spin up, then all the bunches that I inject with spin down will slowly depolarize, go through 0, and repolarize with spin up. So I still don't have bunches with spin down. So what we have to do is simply we have to replace the bunches frequently enough, faster than the Sokolov-Turnoff time, to keep them all, to have bunches with both spin directions in the machine. So this is basically what that looks like. So this is just schematically shown here. So let's assume with Sokolov-Turnoff and also all kinds of depolarizing effects that are due to imperfections of the machine, my asymptotic polarization is 30%, which is really conservative. We do much better than that. So that's what I get, what I would get if I just left the beam alone and didn't replace anything and waited long enough. So now I inject a bunch with 85% polarization here. And of course, it's also time. It depolarizes then. It wants to go towards this 30%. But when it reaches something like 70%, I kick it out, inject a new bunch here. And that's how I get 80% average polarization. It's time averaged over this bunch or this bucket, this place in the machine. And of course, I have 1160 bunches in the machine. It's also the average over all the 1160 bunches at any given time. I always have 80% polarization. If I inject a bunch with negative 85% polarization, then the decay happens faster because the equilibrium is here on the positive side. So my slope is steeper. I just have to replace them faster. So that's why I get this faster sawtooth here for negative than for positive polarization. So how do I do that? I have to have a polarized injector that can deliver bunches. I have to deliver 1 bunch per second to replace the bunches in the electron storage ring continuously all the time. So this is one of the biggest changes we made over the last year or year and a half. Originally, we had this rapid cycling synchrotron in the collider ring, in the collider tunnel. And that seemed to be a good idea until it wasn't. Problem is basically that was brought up by our magnet designer. So we had this ring in the large 3.8 kilometer tunnel. We had a 400 MeV injector. And then our magnet designer said, well, do you guys even know what you are asking me for? So you want to operate this big ring at 400 MeV. That means your dipole field is only 50 Gauss. You want me to build the dipoles with a field quality of 10 to minus 3. Now you take your nice 10 to minus 3 dipoles, put them in the tunnel. You have an earth magnetic field, which is half a Gauss. That's 1%. Why do I have to build these beautiful, perfect magnets? And then you put them into this mess where you already get 1% of external field. So it took us a while. Basically, there was some evolution there. First, we increased the injection energy into the ring, so we got the field higher. Then we had some ideas for some special magnets that wouldn't have that problem, and so on. And finally, we decided to just take it out of the tunnel because the tunnel also became way too crowded with an additional ring in there. And that's why we have it here. So now what we want to do is we have an electron gun here, a polarized electron gun. We send it through a Linac, 750 MeV. That's a very conventional copper Linac, so-called S-band. It's like the Linac at SLAC, for example. And we send 28 bunches there per second, each one nanocoulomb. We accumulate them in the bar, the beam accumulator ring. And so we get 28 nanocoulomb, that's what we need in the electron storage ring per bunch. Then we accelerate them here in this rapid cycling synchrotron to 5 to 18 GeV. And then we have this swap out injection here with the electron storage ring. Okay, let's come to the business end of the machine. So a few words about, a few slides about luminosity and focusing. So luminosity, I think you all know the luminosity formula is inversely proportional to the spot size at the interaction point, right? The smaller the spot size, the denser the beams, the higher the luminosity. However, at the interaction point, the beam size times the beam divergence is constant in each plane. So that's basically what this emittance that I've been talking about is showing you. So for a given beam with fixed emittance, the smaller beam size at the IP means a larger divergence. The more I squeeze my beam together, the larger it goes as I go away from this interaction point. So what happens there is my beam, of course, is focused by magnets. So if I squeeze it here, then it gets larger here. At some point, it just doesn't fit into my focusing magnets anymore. So that's my limitation here. The magnets have to have larger and larger aperture, basically, while the focusing strength remains the same. So there's a technical limit, so I can't do that. What that also tells you, of course, we want to put these focusing elements as close as possible to the interaction point, because if I move this magnet from here to here the beam is only half the size. So the closer I get, the easier it gets to build these magnets. Okay, one other feature of the EIC is we have these very different energies of the electrons and the hadrons. So the electrons 5 to 18 GeV, the hadrons or protons 41 to 275 GeV. So if I shared my focusing elements, my focusing magnets between electrons and hadrons, they would just not have the right strength, right? If I send the electrons through the hadron focusing magnets, then they would be totally over-focused and I could not get the stable optics anymore. If I sent the hadrons through the electron focusing elements, they would barely feel them, so that wouldn't help me. But I want to have my magnets, both of them, as close as possible to the IP. So I cannot focus the electrons first and then separate the beams and then focus the hadrons. So the only reasonable way to do that is by having a crossing angle. So I cross at an angle, but there is a problem with that. So if I have head-on collisions shown here schematically, that every particle in each beam potentially has a chance to collide with every particle in the other beam. Right? So they go through each other. So a particle here at the head of the green beam could collide with a particle here, 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 here. So that gives me the high luminosity. So now if I collide at an angle, and this is more like what the bunches look like, I couldn't find the same picture basically for both of them. So you have these long skinny beams here, they collide at an angle. And what happens, of course, is that the particle that is here in this blue or purple beam has only a chance to collide with particles that are somewhere in a slice around here in the yellow beam, because they cross through each other. It will never see the particles back here. So that reduces my luminosity. And if you simply calculate that, say the proton bunches are something like 6 centimeters long, they are 100 micrometers wide, and they collide at an angle of 25 milliradian, then each particle can only interact with a roughly 4 millimeter thick slice of the 6 centimeter long oncoming bunch. So that's a vast reduction in luminosity. So we have to counteract that. And the trick here is that there is my animation, what we call crab crossing. So the bunches come in here, the electrons from here, the ions from here, and then there is a cavity that gives them a transverse kick to head and tail of the bunch. They tumble around, and once they get to the interaction point here, they are lined up with each other. There's perfect overlap, and that's how I compensate for my crossing angle. But of course, nothing is perfect. The problem is I do that with cavities, so they have a sinusoidal signal, a sinusoidal kick. The bunches are not infinitely short. Actually, their length is not short, really, compared to the wavelengths of my RF cavities. So what happens here is my bunches get this kind of, I don't know, it's not even a banana, it's 2 bananas or whatever. They get this odd shape here. So head and tail of the bunches are not along this midline here. They are deflected to the side when they see the red electrons here. And that means, of course, I have some luminosity reduction, but the real problem here is some beam dynamics effect. So I have to compensate for that. So what I do is, instead of only having 197 megahertz crab cavities, I add a second system here, harmonic system with 394 megahertz to straighten out the kick. And the other alternative would be to just reduce the frequency of the crab cavities, but 197 megahertz crab cavities, these are superconducting cavities made of niobium, and due to their size, basically, the size is limited by the size of the niobium sheets that are commercially available. So we cannot build larger cavities because we just can't get the niobium for them. Okay, here are a few pictures, basically, what this thing looks like. So, so we have not only renderings already, that's a 197 megahertz crab cavity string, but we also have parts already. They are built at Jefferson Lab down in Virginia. Okay, so now the detector itself, or the interaction region itself. So as I said, it's based on a crossing angle, 25 milliradian, that is compensated by the crab cavities. We don't have any electron dipoles within about 30 meters upstream of the detector because, again, an accelerated electron or deflected electron generates synchrotron radiation that would go through the detector, would potentially harm the detector if it doesn't stay in the beam pipe. So we have to avoid that. Best way to avoid that is to have the dipoles as far away as possible. We need large aperture superconducting magnets to accommodate the forward scatter particles here. So this is the hadrons coming in from here. And the synchrotron radiation that is generated at the quadrupole upstream of the detector in the electron ring. So here we need the large apertures. And yes, the colored boxes here are the apertures of the magnets, not the outside. So that's how we draw these things. So now let's go through the elements of the interaction region a little bit. So the physics requires that we can detect particles with transverse momenta from 200 MeV over C up to 1.3 GeV over C. They are detected by Roman pots down the beamline, so they are here. That also constrains, the idea of the Roman pots also constrains how much we can focus our beam at the interaction point, because the Roman pots can only get to within 10 sigma of the beam. So if my beam itself has a large divergence, then 10 sigma here corresponds to a large transverse momentum. So I can't get down to 200 MeV anymore, because 200 MeV, a particle with a transverse momentum of 200 MeV would be inside the beam. So that limits me there. And I also have to accommodate the 4 milliradian neutron cone in the forward direction. Now, the most interesting magnet here in this interaction region is the forward spectrometer. That's the B0 PF magnet. So that sits right outside the central detector. It's a large aperture combined function magnet with detector elements that are actually inside, and an electron quadrupole inside that hadron magnet. So this is what that thing looks like in a cross section. So I want to have a spectrometer magnet for all the scattered particles here, and this area here is filled with detector elements. The hadrons go through here, but the problem is I have to send my electrons also through there. So if I made that simply a dipole magnet, then my electrons would see this large dipole field from this magnet, from the spectrometer, would get deflected, so I don't want that. So the trick is that the spectrometer is actually a quadrupole magnet, and it has additional dipole bindings, a dipole coil. So I shift the magnetic center of this quadrupole over to where the electrons go through. They don't go through the mechanical center of the magnet. So the electrons only see a quadrupole, but they don't see the dipole field. And that's how they survive this. I can actually use this quadrupole field to focus my electrons already. So it's nice and close to the detector, so that's ideal. All right, and now synchrotron radiation. So that's here the electron downstream end of the interaction region. The radiation gets generated by the focusing quadrupoles here that are upstream of the detector. It has to pass through the detector and then through these magnets downstream of the detector until I get to some synchrotron radiation absorber that is far away, and that makes sure that nothing gets backscattered into the detector. And finally, I have to measure my luminosity, of course, in this machine. So the luminosity measurement is based on beta Heitler photons. Essentially, that's bremsstrahlung that is generated in the interaction of the electrons with the protons or the hadrons. Beta Heitler photons, they of course travel with the synchrotron radiation fan. I have to separate them from the synchrotron radiation photons. Fortunately, their energy is much, much higher than the synchrotron radiation. So I just send these guys through a window that does not pass the synchrotron radiation. The window converts these high energy beta Heitler photons into plus and minus pairs, and those I can detect, and that's my luminosity signal. So beta Heitler is a process that can be calculated to high precision in QED. So that's an absolute luminosity measurement. You don't have to do any scans of the two beams relative to each other to calibrate your luminosity measurement. This is really, it's physics, it's basic. All right, and finally the spin rotators. So I said before that we have spins up and down in the machine, and you want longitudinal spins at the interaction point. So we have to rotate the spins, and that is done by helical dipoles in the hadron ring. Those are the same as in RIG. So that is shown here. So these grooves here show the coil windings of these dipoles. So it's a little bit of magic that these dipoles create this spin rotation there. For the electrons, it's a little bit more straightforward. We use solenoid magnets. So you come out of the arc with a vertical spin. You go through a solenoid magnet. So you get a precession around the longitudinal axis of the solenoid spin. And when you exit the solenoid, it's radial. It's horizontal to, let's say, the outside of the ring. And then after that, we have the regular dipoles, the rest of the arc, basically, until we reach the interaction point. And these dipoles then create another precession, basically, around the vertical axis. So then when I reach the interaction point, my spin is longitudinal. On the other side of the interaction point, I do this the same in reverse. So I have, again, my dipoles. They rotate my spin into the radial direction. And then I have a solenoid that rotates them from radial to vertical. So in reality, it's a little bit more complicated because the solenoids, they couple my beam motion between horizontal and vertical motion. So I have to decouple that. We split each solenoid into two slices, and we have quadrupoles in between, and they do the decoupling. All right, and there's my summary. So the EIC is a very complex, challenging machine. I hope I made that clear. There's a lot more to it. I could talk about it for hours or days even. It's a high luminosity machine. It's polarized beams. Both the electrons and the protons are polarized. We have crab crossing, beam cooling, a large energy range, flat hadron beams, and the list goes on and on and on. One thing, it meets the requirements that are laid out in this mission need statement from DOE. So this is really the machine that they want. We made a couple of crucial design changes, notably taking the RCS out of this big tunnel and putting it into a small tunnel that we have to build. The design is well underway. We are preparing for critical decision 2 and 3. 3 means start of construction. And CD4, which is the end of the project, start of operations, is envisioned in 2036, I think, is more realistic now. 2034 we won't make. All right, that's all I have. Thank you.
Questions or comments?
There must be questions.
Slide 6, you showed luminosity changing with center of mass energy. Yeah, so it is increasing till like 110 or something GeV, but after that, why it is decreasing? Is it like you're not able to?
Right. So I increase the energy by increasing the electron beam energy. And synchrotron radiation scales with gamma to the 4th. So I increase my synchrotron radiation power goes with gamma to the 4th. So I increase my beam energy from 10 to 18 GeV. That's a factor of 1.8. 1.8 to the 4th is 10 practically. And that's why I have to reduce my electron beam intensity by a factor of 10. You can play a few tricks here that we don't quite lose a factor of 10, but basically that's what happens there.
On slide 18. Yeah, previous. Yeah. So here you said like this polarization decreases and then you re-inject the beam. So there will be a time lag. How you manage that?
No, there is no time lag. It's the same kicker. So the beam comes around and it arrives at the kicker, the bunch, right? One packet in the beam. They are spaced by, what is that, 10 nanoseconds? I have a fast kicker, the bunch arrives there, I kick it out, let's say I kick it to the right, and the same kicker kicks a bunch that comes in from the right and kicks it onto my orbit. So there is no delay. So that is, even we don't want any delay there. It has to be as transparent as possible to the hadron beam. Otherwise, we disturb the hadron beam too much.
Thanks.
Can you explain the stochastic cooling again? I understand the electron cooling when it interacts with the electron and it's just getting a cool path to cool down. But where exactly and how exactly the cooling is happening in case of the stochastic cooling?
So you correct the measured offset of the particles. Right? If you measure the whole beam, the whole sausage at once, right? Then yeah, if you measure anything that's not zero there, you correct it once and that's it. Right? When it comes back on the next turn, it is at zero, there is no signal anymore. But the trick is that I slice it. And if I have short enough slices, then I have a manageable number of particles in there. And if I measure those, then there is a tiny deviation from zero. And that I correct with my kicker. So if the same slice, the same particles came around again, they would still be at zero. But the trick is mixing. They move longitudinally between the two slices. They move back and forth. And that's basically the stochastic part, basically, that they move and now I slice again and I have a different subset of particles. They were not measured together before, right? So I measure again, there's still tiny, very tiny deviation from zero that I can detect and correct again. And I have to do that millions of times, of course, but that's how it works.
Okay.
So for Rick to achieve like the polarization, there was that helical magnet, the Siberian snakes.
Yes.
Will EIC still be employing that method or?
Yes.
Oh, okay, cool.
Yes, we will even install more snakes. So Rick has 2, and we will install 4 more snakes.
Okay.
So we will take the 2 snakes from the blue ring, install them in the yellow ring, and then we have the spin rotators from the blue ring, and we can convert them into snakes. Basically, we have to, each snake consists of 4 magnets. And each spin rotator consists of 2 magnets. And we have to arrange these 4 magnets differently, and then the spin rotator becomes a snake.
Thank you.
Could you talk a little bit more about injecting the polarized hadron beam? How do you get the hadrons polarized and then inject them and keep the polarization?
Okay, so it's the polarized source is like magic. No, I mean, I'm not an expert on this, but how does that work? It's long ago that I did that. So you have to create them at the source, they are polarized, and you have to preserve it. It's complicated. There are optical transitions and stuff like that. So it's interesting. It's atomic physics in the end. It's really cool.
Polarimetry, and I guess some of this discussion is going to be there. So Monday we have hadron polarimetry.
That's Frank. Frank
Ross
Rodman.
is going to talk about. Ross Cordes is going to talk about this. It's his task. So we probably will defer the question to him. And explain how the magic happens. Yeah, go ahead.
And then when you're talking about the like slices, are these inside of an individual bunch?
Yes.
Okay.
Yes. Each sausage is a bunch, and yes, and I slice them electronically. So I measure whatever. I mean, the bunch is 6 centimeters long, and I measure every, let's say, 500 microns or whatever the number is.
I know I have to run to PNL of the review, but we still have 5 minutes before the coffee break, so I'll probably ask a couple of questions. So for the electron ring technology, are you basically using the same technology as JetLab is using? Is it somehow drastically different? Or
I'm not sure what you mean by the same
um,
technology.
so they have the cavities for the rating, and then they basically loop.
Yeah, but it's a ring.
Like the same sort of way of.
Well, I mean, JLab is a LINAC,
Yes.
right? It's a recirculating LINAC, and this is a storage ring.
Okay, so it is.
So that's different.
It is different. Okay.
In that sense, it's different.
And imagine we fast forward 10 years. Okay, so it's 2026, if you remember. So they all now faculty and they students come here for 2036 cfns summer school, physics of the electron-ion collider, and CT4 finally is there, and you're presenting the lecture. What beams we are running, what energy we are running, when we start. What is it a decision to be made based on some factors, or we know already what the project starts with?
It's still being discussed. So what we would like to do is we would like to start with an energy and or a species that we can keep at the center of the beam pipe or close to the center of the beam pipe. Because this is not trivial to do this radial shift. It's just an additional thing that has to be commissioned. And we would like to keep that for the second or third year. We don't want to start with that.
130. And it's for the.
It's 130 GeV protons. And then for heavy ions, you have to.
Right.
I think one talk was that we use niobium.
Yes.
So niobium would end up close to the center.
And for the electrons, is there any sort of preference energy for the electron beam?
Not real. Yeah. Okay. Okay. Now it's getting really complicated. So we would prefer 10 GeV anyway, because that's also our high luminosity point, right? That's we just made a change, or in the process of making a change to the energy. So instead of 10 GeV, we propose to go to 9. As I said, the synchrotron radiation power goes with gamma to the 4th. So this 10% change saves us 35% of synchrotron radiation power. 35% of 10 megawatts is a lot. So that's what we want to do.
Homework, 9 GeV electrons and 130 GeV protons was the center of mass energy.
So when you do the electron cooling, so basically the hadrons are basically very high energy at this point, maybe, I think. And then the electrons can't be that high. So
they have to have the same gamma. The gamma has to be the same. They really merge. So the energy is different by a factor 1,836 if it protons. Right? But the gamma has to be the same. They travel together and they exchange energy. The electrons heat up, right? In this, and the protons or ions cool down. It's two gases, basically.
yeah, because I was thinking like, how do you prevent like inelastic collisions from happening there? Because they're
traveling together. So the relative velocity is close to 0. That's the whole idea.
Okay.
On this slide, you talked about we have to adjust the hadron orbit to make sure that everything is in sync. And you were saying that you go 20 millimeter the center for 130 in either direction. So I'm just curious, what's the typical size of the beam when they collide or at the interaction point? Hadron.
At the interaction point, beam width is 100 microns and the height is 10 microns.
And this adjustment where you say about 20 millimeter adjustment, this is at the...
This is in the arc, where the beam is larger. So there the beam is roughly 5 or 6 times larger. So you have a 500 micrometer RMS beam, right? And we want 10 sigma. So that's 5 millimeters, 5 millimeter radius.
All right, before coffee break. So this afternoon we have lecture by Abhay Deshpande, who is going to tell us perspective of the AC. After the lecture, we'll have school photo. So be here unless you want not to be in the school photo. You want to be in the school photo. So let's thank Christoph once again.